All right, it's time for the free response for the electricity and magnetism exam. But first, this video is brought to you as a public service by World's Finest Physics, which is pretty much me. So, we have professional development opportunities for physics and math teachers. You're probably a physics teacher if you're watching this. And since this is electricity and magnetism, I'm not sure if a an in-person workshop in Frisco, Texas might be interesting to you, but we're going to mostly focus on mechanics topics. It's for anybody who teaches these topics, any level, not just AP. And we're really going to hit lots of cheap and easy to execute hands-on activities, really raise the level of inquiry, of engagement, of just having fun and getting out the students out of their seat. Tackle difficult things like how do we think about maybe energy of systems better. Newton's third law is one of them, better remediation techniques. Heck, if you're interested in pitching this to your math teachers, it's not exactly the same thing, but it's a lot of interesting stuff for math teachers the week before. It's got to be in person because, again, it's a lot of hands-on. And think about it. If your students' math teachers are doing a better job of teaching and engaging students in math, doing performance-based assessments, doing real-world connections, engaging in experimental design, but in a math setting, then that's just going to help you. So you have everything to gain from your math teachers coming to this, and they have a lot to gain from it too because they can make their math class a lot of fun. And then if you're a student watching this or a parent, then just know that we also provide in private online tutoring for these kind of subjects and more. I probably should say and more there. All right. Special thanks to the College Board for writing these questions, and special thanks to Golden Corral for making delicious food. All right, so here we go. Students perform an experiment to determine the value of vacuum permittivity epsilon naught. Sphere 1 is non-conducting, it's charged, insulating rod, okay. All right, so it's a rod and two balls hanging down is what we got to deal with here. Sphere 2 is hanging from a string, no mass, length L. Sphere 1 is brought near and without touching. It's very important. We should not be touching things, right? Okay. Sphere 2 is shown. Do you have any words for our audience? No, get away from me. Looks like a microphone to me. That's actually what I thought when I wrote this question the first time. I was like, yeah, it looks like you're trying to interview somebody. Anyway, so there you go. Equilibrium is established, have the same vertical position, horizontal distance D apart. Okay, all that, and we don't even use the front page. On the following dot that represents which one is sphere 2, that's the hanging one. Draw and label the forces, not components. Force, tension. Mg, force, electric. Okay, I hope that makes sense. Note to y'all, if you didn't know this, then maybe I should say this in each of my videos. I should have said it in the other video for mechanics. If there's a dot on the page, your students need to make sure that the arrows physically touch the black dot. If there's a gap between the arrow and the dot, no matter how small, if there's a gap, like right there, it looks like there's a gap there, so I'm going to kind of fill that in. The readers are instructed not to take it, not to consider it for grading. All right, derive the relationship between the distance D and the angle to show that D equals that. So here's what I'm going to say. What I'm going to say, where's the angle located? So on the vertical. So there's the angle right there. So what I think I'm going to do is I'm going to create what I call a balanced forces triangle. This is a technique you may not use with your students, but you never know, it might be helpful. So what you'll notice is that if I take those three forces right there, theta, then I can actually form a complete triangle out of them, because if the forces balance, which they do, this is equilibrium, then the all the vectors add to 0, which means they form a closed figure, right? So what I can say from this is I can say tan theta, there it is, tan theta is the electric force over the gravitational force, and the electric force is K, big Q, little q. Which one is which? That's little q and the big Q, okay, over distance squared. So I'm going to plug that in here. Tan theta equals KQQ over mg and distance squared. Okay, just plugged in. So now let's get the distance by itself. Distance equals KQQ over mg times the tangent of theta. And then you can square root. And then, yeah, the K is really 4 pi epsilon naught in the denominator, QQ over mg tan theta. Okay. These values are collected in one trial. Calculate the expected force of tension exerted on sphere 2 by the string. Well, that's just the Pythagorean theorem, right? So force tension is the square root of mg all squared and kqq over distance squared all squared. So let's start with the mg. The mg is going to be hey, oh, wait a minute. Okay, so I can't do that because I don't have that information. What I really should be doing is saying that force tension and the electric force have a relationship that is going to be sine theta. So the electric force over force tension equals sine theta. So force tension is really the electric force over sine theta. That's going to be KQQ over distance squared and sine theta. So it's going to be 9 times 10 to the 9. The Q. Oh, 6 times 10 to the negative 8th squared. They're the same. Excuse me. Okay, there you go. D, 0.057 squared, and the tangent of 12 degrees. Let's make sure our calculator's in degrees. Oh, whatever. What is that crap? Where's the mode? There it is, in degrees. Okay, so 99 times 6e negative 8 squared over 0.057 squared times the tangent of 12. Okay, so I'm going to get a force tension of 0.0469 newtons or something like that. All right, that's what I got. All right. The students vary D and measure theta after equilibrium is reached. They make that graph right there. Here's my pink ruler. So I'm going to use a pink pen with the pink ruler. Okay. By the way, if you're wondering, this is set number 1 that I'm working on right here. I think I have it in the corner there. I have not seen these in advance other than to write the word set 1 and set 2. I did not look that closely at these, except I did recognize that this diagram, I was like, hey, he's trying to shove a microphone in the face of that other sphere. I was like, that feels familiar to me. That's why I pulled up that one from before. I wrote it like more than 18 months ago, so I actually have no memory of this question other than the fact that it felt a little familiar. Best fit line, about same number of dots above and below. Using a best fit line, calculate experimental value for epsilon naught using that and that. Okay, so I'm going to use this equation. D equals QQ over 4 pi epsilon naught mg tan theta under the radical. And so what I'm going to do is I'm going to square everybody. Let's square the D and let's remove the radical, 4 pi epsilon naught mg tan theta. Okay. And now what I'm going to do is I'm going to say that D squared times tan theta is QQ over 4 pi epsilon naught mg tan theta. Oh, not tan theta though. Okay, and then this is really the same thing as dividing by 1 over tangent. Okay, so this is the rise, this is the run, so that is the slope. So I'm now going to calculate the slope, and I'm going to use that point. What other point should I choose? I guess I'll just use that point right there. Okay, so the slope is going to be 0.004 minus 0 over 6 minus 0, which is whatever that number is. Okay, and then we're going to set that slope equal to QQ over 4 pi epsilon naught mg. I'm really going to do this. I'm going to say epsilon naught is QQ over 4 pi mg. So times the slope, right? I just cross multiplied, right? So that's going to be Q, all right, 6 times 10 to the negative 8 all squared over 4 pi. The mass is 0.005. G, I'm just going to make 9.8. And the slope is whatever 0.004 divided by 6 is. Okay, so let's see how I do here. 6e negative 8 all squared. Okay, we're working down here in the corner. Divided by, in parentheses, 4 pi times 0.005 times 9.8 times 0.004 divided by 6. It's supposed to be 8.85. Say that pretty close. Epsilon naught, 8.77. 10 to the negative 12. Farads per meter, I guess is what the units are. Okay, it's something else. It's actually on the formula chart. So your students should put units on everything that's a number. All right, so there you go. The students modify the experiment by replacing sphere 1 with a conducting sphere 3, same size and charge. The circle in the following figure represents sphere 3 when spheres 2 and 3 are at equilibrium. Okay, so sphere 3 is replacing sphere 1. I'm trying to shuffle these pages here. It's like doing my taxes here. Okay, so if this was conducting, then the highest concentration of excess positive charge would be over here. Explain your reasoning. The positives in sphere 3 are on the surface and will gather on the side opposite sphere 2, which is also positive. Okay, when the centers of the two spheres are d1 apart, the string makes an angle at theta 1. In the modified experiment, the new theta is going to be less than the old theta. And why? Because now sphere 3 has charges farther away than sphere 1 had. Okay, so like sphere 1 might have been like this, but sphere 3 is probably more like this. So because the charges are farther away, then theta 2 will be less, since sphere 2 must get closer to the center of sphere 1 to get closer to the charges that moved away. And by the way, can I just tell you, that's the smart way to present these kind of questions with the alligator symbols, right? Not is theta 1 greater than, less than, or equal to theta 2. Like, that's really confusing. But presenting it this way, that's a smart way to do that, College Board. Did I actually do that? Did I do that on this thing right here? No! Oh my gosh, look at that. I did greater than, less than, or equal to. Shame on me. That's a bad way to do it. I'm glad they don't do that anymore. They should stop doing that and start doing it the exact way that they did it here. That's the nice way to do it. Please keep up the good work. Rare compliment from Friendly to the College Board. Okay, now, this is set 2. They're going to try and get the epsilon naught, but this time they're using a spring, okay? I think I've probably figured it out just from that picture. Okay, so sphere B is going to experience an mg and an electric force, and I'll bet you there's a spring force, like a kx or something like that. Are they calling this y? Compress the distance y. Okay, well, ky then. Okay, it's like jelly, right? I don't really want to think about that. Derive a relationship between y and h. H is the distance center to center. Okay, so I'm just going to write an equation here that says the electric force plus mg equals ky. All right, and I think I'm supposed to call that ks because that's the spring constant, which is not the same as the Coulomb's law constant. Okay, so okay, so what's the electric force? K. What are the names of these charges? QQ. All right, QQ over H squared plus mg. Okay, do I have any other weird subscripts here? Maybe a capital M is what this should be, okay? Equals K spring Y. So then Y would be K. Oh, no, there it is. There's the Coulomb's law constant, and then there's the spring constant. Okay, I did not write this question, so whoever did, good for thinking for that. And then the K is really the same as 4 pi epsilon naught in the denominator, spring constant H, not the same as the Coulomb's law constant, mg over the spring constant equals Y. All right, the lights just went out here in Georgia, so that's a joke. I'm actually in Texas. But it's like the lights that went out in Georgia. Never mind, just shut up. Just shut up and stop making fun of me. Okay, the students collected data of Y versus 1 over H squared, and it has a loud and conspicuous intercept. Wow, I wish I didn't have to draw this best fit line, and yet here I am. What a terrible... Did anybody actually do this? I sure hope not. Okay, here we go. I'm going to draw the best fit line now. Okay, that's the sound the best fit line made. Okay, so what I want to do is I really want to write this again. Y equals QQ. I'm basically reading it off of here. Over 4 pi epsilon naught KS times 1 over h squared. Okay, you see how I'm rearranging the h squared there? Plus mg over ks. This is y. This here is slope. This is the x. And this is the intercept. Draw a best fit line. Using the best fit line, calculate the epsilon naught. So the slope is going to be QQ over 4 pi epsilon naught spring constant, which means that epsilon naught is QQ over 4 pi, the spring constant times the slope. Now, what is the slope? The slope is going to be, I'm just going to use that point and that point right there. So it's a rise of 0.02 over a run of 30, whatever that is. Okay, so 2 times 10 to the negative 6 squared over 4 pi, the spring constant 25, that's a pretty decent spring right there, 0.02 over 30, okay. So here we go. I did not write this question, but whoever did was obviously thinking of me. Thank you so much. I'm so honored you were thinking of me when you made this question, because you're thinking of the question that I did send you and you used it. Good for you. Ooh, that's not good. That is a bad thing. That is not anything close to epsilon naught. What did I forget? I forgot something. Must have forgotten something. Okay, that's QQ. The slope, that's 1 over h squared. Okay, let's see here. There's a 4 pi k, and the slope like that. Why do I know the h is there? All right, so 2e negative 6 squared. That would get it. Well, maybe that's it. I don't know. I mean, it should be 10 to the negative 12. This is about double what it should be. Did I screw this up that badly? Oh, no, because the slope is actually 0.04. There we go. Okay. So the slope is actually 0.04. That goes teaching never to, don't ever count all the boxes. That, I'm going to take that. Okay, epsilon naught, 9.55, 10 to the negative 12. That's from here. I don't have the formula chart in front of me, so I don't know what the epsilon naught is lifted on at the formula. All right, experimental value for the mass. Okay, so the intercept is mg over ks, right? It's right there. So then the intercept's like 0.12. I mean, I'm just reading it off right there. Equals m. I'm going to use 9.8 ugly numbers over 25. So then I'm just going to say, okay, 0.12. 0.12 times 25 over 9.8. You know what? This might have been prettier if I had used 10. What if I had used 10? Oh, it would have been really pretty. Okay, so 10. All right, so the 10 is 0.3 kilograms. That's that. Okay. Oh my gosh, I have so many papers here. Okay, the students modify the experiment by replacing non-conducting sphere B with conducting sphere C. What was B again? I can't remember. All right, B was the, what happened to my front page of this question? Why is this question so many pages? All right, so B itself is now a conductor. As A is brought near C, compressing spring. The original experiment, there's an H. The modified experiment, when they're the same distance apart, it would be less force because it's farther away. So less force means less compression. Okay, so in the conductor, the positives move down away from sphere A. So this was sphere B before, meh, 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 meh. And then this is sphere C, meh, 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 right? Okay, so at the same height, right? The F is less since the charges are slightly, the electric force, farther apart. So less spring compression. Okay. Sphere C is then grounded with a wire, so it's not going to be charged anymore. On the following figure, draw an arrow indicating the direction that the platform will move immediately after being grounded. Are you serious that that's just that? It doesn't have a charge anymore. So now it does not have that downward force. So now that it does not have that downward force, really the way this should have been drawn is it should have been drawn like this: MG, FE, and KSY like that. So without that, now you have an initial upward net force. Okay. All right, that was all there was. Okay, that's all there was to it. All right. So you got your X's and the O's. Okay, so two horizontal the resistor resistance R connects the rails. Ideal spring. This is two springs. Wow. If you're taking the E&M exam and you don't know about springs, you're like fucked. Oh my gosh. Oh wow. That's a lot of springs, people. How many more springs are there on this? Okay, if there's an inductor, I'm going to be smart enough not to call it a spring. Wow, set one. No, actually, I take it back. Because set two had the spring before, and this is set one. Okay, so each set had to deal with the spring. Okay, I thought it was the same set that had the two springs. That would have been really ugly. Okay, spring is free to move. A conducting bar is placed on the rails, at which point the friction is. Oh, wow. It's a bulleted list. That can't be good. At time 0, the bar is released from rest. At time T1, the bar loses contact with the spring. At time T2, the bar enters and travels through the magnetic field into the page. At time 3, the bar enters the different other region out of the page. No magnetic field. Consider this. Gosh, freaking, I got to label this. T0, T1, T2. T3. I'm going to lose track of all this. T4. Wow. This is a lot. Okay. On the following diagram, why is it called TB? Okay, yeah. Draw an arrow indicating the direction of the net force exerted on the bar. Easy. Okay. Now, why has it got to be that way? I'm not even going to go through this, the Lenz's law, like rules, left, right hand rule, induced current. I'm not even playing that game. I'm just going to tell you right now, and this is Lenz's law. If the EMF is induced by a motion, then that current will have its own ILB force that opposes. So it didn't matter whether this is X's or dots. All that mattered is that the bar was moving to the right, so it has an ILB force pointing to the left. Okay, the speed of the bar is that. Calculate the current in the bar. Okay, so this is one of those moments where I'm going to say that flux is equal to B times area, which is B times L times X, where X is whatever that is. Really, let's say X is just whatever this is. So we're only taking that area right there, right? Now, EMF is d flux d time, which is BL d distance d time, which is where you get BLV from. And then current then is EMF over resistance. That's Ohm's law. BLV over R. So the B, can you imagine flipping this much back and forth between pages? B, L, 0.4, V, 0.25. Oh, V over R is 0.3, okay? So here we go. Yeah, stop. 0.5, 0.4, 0.25 over 0.3. We get 1.6666666. No, 0.1666666 amps. Calculate the magnitude of the net force. Force would be equal to ILB. So that'd be 0.1666666. What was that L? It was on the previous page, 0.4. What was the magnetic field? 0.5. Okay, so let's take this number times 0.4 times 0.5, and we get an even uglier number. The force is 0.033 newtons on the following axes. Oh my gosh. Okay, let's pay really close attention here. Graph the speed of the bar as a function of time t. Okay, well, you had to know mechanics to do this part. You had to know that while this is while the bar is touching the spring, this is actually 1/4 of a simple harmonic motion period. That is 1/4 of sine from SHM. All right, constant velocity. This is Newton's first law. There's no forces. And now for the part that's going to make you pissed. This is a decaying exponential, and still is, even as the direction of the magnetic field changes, only because the magnitude, the strength of the magnetic field was actually the same. The direction, Lenz's law could not have given two shits about the direction. Can I just tell you? Now, the direction of the current will reverse, but will reverse very suddenly. So yeah, that's a decaying exponential right there. That's a e to the minus t over a time constant type thing. Okay, I'm going to go ahead and not explain to you why that is. If you're mad enough, you can leave some comments that I can ignore. Okay, the scenario is repeated, but an additional resistor is shown. What's the total resistance? Determined. I don't have to show work. 0.15 ohms to identical. I guess I am going to show work after all. Identical resistors in parallel give half as much resistance. Okay, in the original scenario, the acceleration of the bar after the bar enters the magnetic field is that. In the new scenario, the new acceleration is actually greater. Okay, so this would be an example of the bad way to do it, right? Remember how we talked about the good and the bad way to do it? So let's review, College Board. This is not you, the teacher, watching this. This is the College Board who's not watching this, because if they did, they'd be pissed that I'm showing all these first drafts of the questions I've written for them. I've got your money already, and you ain't getting it back, by the way, people. Okay, so College Board people, if you're going to write these things, this is the way to do it. So it should have said A original greater than A new, A original less than A new, or A equal. That's the way it should have done it. Okay, so A new is greater than A original. Now let's talk about why that is. The reason why is because the EMF, which is BLV, is the same. It was the same initial velocity, right? The current, EMF over R, is more. Why? Because there's less total resistance in the circuit. The forces ILB is more. Why? Because there's more current, like we just said. And then force equals MA, so A is more. I feel like I don't have to drag that out for you. Describe a modification that will result in a smaller potential difference across the original resistor. Okay, well, how about less magnetic field? How about a shorter distance between the rails? Hey, here's an idea. How about a looser spring or more mass so that V is less? Oh, there you go. All right. Now, this looks awfully familiar to me. Why the hell would you be putting dots here? Why would you put dots there when you know what you mean to say is that the magnetic field points up? Now, that's not my fault, because I put the arrows pointing up right here. Okay, I did it right. Okay, do you all see this? I want to make sure you know that I did not screw this up. They did. Why would you put dots there when the up arrows worked perfectly good? And then you can tell that they modified it. They didn't have the upslope at the end, right, like that, but they added this B2. Why can't you put the up arrows there? Who, what? Okay, so at time zero. Okay, at time 1, the bar reaches position X1. Okay, so time 0, time 1, time 1. Okay, at time 2, the bar reaches position X2. Okay, time 2. Okay, at time 3, the bar reaches position X3. Okay, that's the beginning of that, which is going to be meaningless. I can already tell you that. Okay, and then X4 is time 4. The time 4 when we leave the meaningless region. Okay, the bar is at position XB shown in the top view between 1 and 2. Okay. Draw the force on the bar. Again, Lenz's law, it really did not matter. It doesn't matter whether the resistor is here or here. It does not matter whether the magnetic field is up or down. All that matters is that the bar is moving to the right. It's going to have a leftward force. Lenz's law always opposes. It's always going to result in the current or the force that opposes the motion of the bar changing the EMF. All right. So once again, we're going to say, I'm not going to go through the whole reason why EMF is BLV. You can see it from the previous problem. So that over the current. Okay, so this time it's going to be 0.4 Teslas. The length between the rails is now called D, and it's 0.3 meters. And the velocity is 2.5, which I think was the same before. And the resistance is 0.2. So now we're going to say 0.4 times 0.3 times 2.5 over 0.2. And then we get 1.5 volts. And the lights have to go off because it's after school now. I already saw my P1 students. They said that the multiple choice was easy and the free response was insanely difficult. They said the whole free response was rotation. I have a lot of trouble believing that. Okay, volts. No, amps. Sorry, that's a current. All right. The F net, okay, F equals ILB again. So the 1.5, the length of the bar that matters for this exercise is the D distance, 0.3. The magnetic field is 0.4. Okay, so that times 0.3 times 0.4. Okay, so 0.18 newtons. Okay, now this is the part that's going to be different. Now, the V as a function of time is going to increase linearly because if you have a straight slope, you have a constant acceleration on a straight incline. Now, between T1 and T2, you're going to have that decaying exponential happening, and then you're going to have Newton's first law. Newton's first law, because there's no forces. This is an E to the minus T over tau. And then for this part, you're still going to have that. There's no magnetic force because the magnetic field needs to be perpendicular or at least not parallel to the length of the bar. It needs to not be parallel to the length of the bar. That is my story, and I'm sticking to it. The original scenario is repeated, but with a new bar. It has the same mass, but with its own resistance. The new bar is transitions, okay? The total resistance of the closed surface, are you seriously asking me this? It'd be 0.2 plus 0.2 is now 0.4 ohms. Okay, that's a determined. Okay, the new acceleration is now less. The A new is less than A original. Now, why is that? The reason why is because EMF equals BLV is the same, right? The I equals E over R is less since the R is more, right? Okay, the force equals ILB is less because the I is less that we said. And then F equals MA. I think you can figure it out. Describe a modification that will result in a larger induced current. Okay, how about use a smaller resistor? Oh, no, the modification of these things that will result in a larger induced current. Okay, so you can have a higher H resulting in a faster velocity. Okay, that's more EMF, more current. Okay, now I think that if you have more B or D, that's also a higher EMF because the B and the D, which is the L here, which would be more current. Okay, so any of those modifications ought to work. Okay, it's the last two questions. Wow, this is taking a long time. All right, the circuit shown consists of battery EMF E, resistors 1 and 2, which are basically in parallel, each with resistance R, so this is basically just R over 2 is what that's worth. Capacitors 1 and 2 with C and 2C, right, but do not solve a differential equation that can be used to determine the charge as a function of time t. Okay, so I do the loop rule as a sum to 0. So the EMF is going to be positive as I go around this loop. And then we're going to lose I times R over 2. And then we're going to lose the voltage on the capacitor, which is Q over C. So that right there, that's the voltage on the resistor. That's the voltage on the capacitor equals 0. So now to turn it into a differential equation, oops, that's a minus. It would be R over 2 times the current is dq dt minus Q over C equals 0. Okay, on the axes shown, sketch graphs of the surface charge density sigma. That'd be the same as just the charge. It'd be the same shape. And the total power dissipated by the resistors. Okay, so P is equal to I squared R. So really, I'm just going to be graphing basically current. Okay, so asymptote. and asymptote, right? Okay, we're going to asymptotically approach the final charge and the power, which depends on the current. The current is going to asymptotically approach 0. A long time after the switch is closed, position A, the charge on positive plate capacitor 1 is Q naught, capacitor 2 is on charge. At time T1, we move to position B. Immediately after time T1, is the direction of the current in the switch directed left, right, or is there no current? It's going to be directed this way. So in this new circuit, we have a bunch of positives on the plate here and negatives here. And what the positives are going to do is they're going to go that way. Now, I know the positives aren't the actual ones that move, but you know what? I like Ben Franklin, so screw you. All right, so I'm going to say to the right as positive charge moves from the top of capacitor 1 to the top of capacitor 2. And again, moves, positive charge really doesn't move. Heck, I mean, maybe we can just say it's like charge. It goes ahead. Let's just go ahead and just put all this stuff in the sarcasm quotes, right? Okay. So determine the expression for the total charge on the positive plate of capacitor 2 a long time. So here's the deal, folks. When you charge a capacitor with another capacitor, the following things hold. The initial total charge equals the final total charge. So that's Q naught is going to equal Q1 plus Q2. That the before and after the charge is conserved. But the condition of equilibrium is that the voltage on capacitor 1 after has to equal the voltage on capacitor 2 after. Those are the conditions of equilibrium. Now, if Q equals CV, that's the equation that I remember, then V equals Q over C. So Q1 over C equals Q2 over 2C. So basically, we're just going to say that Q2 is twice as much as Q1. So how am I going to divvy this out? Well, Q1 is going to be 1/3 of Q naught, and Q2 is going to be 2/3 of Q naught. These two add to Q naught, and one of them is twice as much as the other one. So the positive plate of capacitor 2 is going to have that much charge. All right, derive an expression for the total energy dissipated in the resistors. Okay, now the energy stored in the capacitor is 1/2 CV squared, but also V is Q over C. So then if you plug that in, you get 1/2 C times Q squared over C squared. So you get Q squared over 2C. Now, before what we had is just capacitor 1 had energy, and its energy was Q naught squared over 2C. Now, after what we have is we have C1 and C2 have energy. Okay, so what are we going to say about C1? It's going to be 1/3 Q naught squared over 2C, and C2 is going to be 2/3 Q naught squared over 2 times 2C, because remember, he has twice. Okay, so now let's take this information and let's Q squared over 2C minus this sum, 1/9 of Q naught, squared over 2C. Okay, that's 1/9 right there. And, okay, now what do we got here? This will be 4/9, but this will cut it down to only 2/9. So this will be 2/9 Q naught squared over 2C. Okay, so it's 1 minus 1/3 of these. So it's going to be 2/3 of Q naught squared over 2C, or in other words, 1/3 Q naught over 3C squared. That is the energy dissipated, is the difference between how much the capacitor stored before and after. With the switch still closed to B, the parallel plates of capacitor 2 are moved, so separation distance increases by a factor of 2. Determine the ratio of the energy stored in capacitor a long time after the plates of capacitor 2 have been moved. Okay, so I'm still going to say the total charge is still Q naught, but the capacitance of 2 is half as much now. Okay, which would be equal to C. Remember, C is epsilon naught A over D. So if you double the distance, that's half as much capacitance. So what does that mean? That means we go from C and 2C to C and C. It's just C and C. So with that being the case, now is C. So now both capacitors are the same capacitance. They must have the same voltage equals Q over C after a long time. So both have the same Q and the same V. So they have the same energy. So U1 over U2 is going to be 1. All right. Did you follow all that? Energy is 1/2 CV squared. They have the same C and V. Or Q squared over 2C. They have the same Q and C, right? It's like all the same. They're identical capacitors now. When is this going to end? How many parts is this? 1, 2, 3, 4, 5, 6, 7, 8. Oh my gosh, 8 parts. It's not almost as many steps as AA. Okay. With the capacitor still charged as in part D, the switch is now closed to position A. Express your answers. Derive an expression for the current I naught from the battery immediately after the switch is closed to position A. Okay, so here's what I'm going to say. So I'm going to say that EMF minus I naught times R over 2 minus the charge on capacitor 1 over C equals 0. The EMF minus I naught times R over 2. Now, the charge on capacitor 1 is half of Q naught because the two capacitors were identical. So it'd be half and half, right? Okay. Now, Q naught over C is actually EMF. So you get EMF. Am I even writing the EMF symbol correctly? I feel like I'm drawing an epsilon naught. Oh, never mind. Okay. I naught times R over 2 minus 1/2 of epsilon equals 0, or E. So half of E equals I naught R over 2. So then I naught is just going to be EMF over R. That's my answer. I don't even know if I'm true. I'm out of brain now, folks. This is problem number 11 out of 12 I've worked today because I did all the mechanics also. Okay. Determine the current I infinity from the battery a long time after the switch is closed, position 0, because now the capacitor is fully charged. I'll bet you it's a determined, so I don't actually have to write this. It doesn't say justify your answer. But the capacitor now being fully charged, there is now no path through the circuit without going through a fully charged capacitor. So the current has to be 0. Now we've got this. We're going to move to position A, right, but do not solve. Okay, EMF minus IR. There's 2 of them. All right, each has a resistance R. Okay, and then minus the Q over C minus another IR. Okay, I'm walking around this loop. So EMF minus IR minus Q over C minus IR equals 0. So that means EMF minus 2R dQ dt minus Q over C equals 0. Hope you don't mind me going fast now just because it's, it's kind of the same problem. It's the same principles. Okay, this is 1/2 CV squared, and this is IR. So this is going to exponentially decay. Yeah, and then this is going to exponentially rise to a final value. Okay, because the voltage rises to an asymptote and the current decreases. At time T1, the switch is closed to position B. Immediately after T1 is the direction current of the resistor is to the right again as positives go from the top of C1 to the top of C2. Okay, an expression of the total charge on the positive plate of capacitor 2 a long time in terms of Q naught. Aren't they identical? They are identical capacitors. So to have the same V after a long time, they must have the same charge. Why? Because V is Q over C, right? Okay, so what was I going to say? So they evenly split up the Q naught. So it'd be 1/2 Q naught. Okay, is it determined? I didn't even have to freaking explain all that. All right, derive total energy dissipated by resistor 1. Okay, so we start with C1 having a U of Q naught squared over 2C. We end with C1 and C2 being 1 half Q naught squared over 2C plus another 1 half Q naught squared over 2C. Okay, so then this is going to be 1/4 of a Q naught squared over 2C plus another 1/4 of a Q naught squared over 2C. So that's 1/8 plus 1/8 makes 1/4. Q naught squared over 4C. Okay, so then that's the before and that's the after. So Q naught squared over 2C, U initial minus U final. Q naught squared over 4C means you're going to lose 1/4 of Q naught squared over 4C. That's how much you lose. Okay, with the switch still closed, the dielectric material is inserted between the plates. Ay, ay, ay. Okay, so C is kappa epsilon naught A over D. So now capacitor 2 has twice the capacitance, right? So the total Q naught is the same, but now capacitor 2 has twice the charge as capacitor 1. So the voltages are the same. Is this after a long time? Yeah, after a long time. Okay, so then charge 1 is going to be 1/3 Q naught, and charge 2 is going to be 2/3 Q naught. That adds the same total Q naught, but the double capacitor has double the charge. Okay, with the circuit, with the switch still closed, a wire of negligible resistance is connected between two corners of the circuit as shown. So what do we have here? We have plus, 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 minus, 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 and then plus, plus, minus, minus. Okay. Derive, this is the complete circuit, isn't it? I'm going to walk around this loop. That's the loop right there. Okay, walking around that loop. Oh, dang. Oh, there's like 2 loops. Ooh. Okay, express your answers to part E in terms of R, C, Q naught, and fundamental constants. Derive an expression for the current in resistor 2 immediately after the wire is connected to this circuit. Oh, because we also have this other thing happening also. Huh. Well, okay. Well, first of all, this is going to be 0. Determine the current after a long time because all the capacitors are now discharged. Okay, but what am I going to say here? I'm going to say that I have something that's kind of like a battery here. So this is R, and this is a voltage of 1/3 Q naught over C, and this is a voltage of 2/3 Q naught over 2C, which is the same. So these two have the same voltage, but this one has some resistance and that one doesn't. So basically what I'm looking at is I'm looking at this. I'm going to say that this is a voltage of Q naught over 3C, okay, like it's a battery. And then, yeah, okay. So I'm going to call that V. All right, so I have capacitor 1, which has a voltage V, and a resistor R, and then capacitor 2, which has a voltage V, okay, and a resistor R, and then this going through resistor 2, which is over here, and then they come back, right? Because the current can split into these two and then come back through there. All right, so how am I going to work this sucker then? Well, I'm going to write 2 equations. I'm going to say that I'm going to say the V. Well, you know what? These are directly in parallel, aren't they? Well, if these are directly in parallel, I'm going to say that that voltage is on. So the voltage on capacitor 2 is equal to IR for resistor 2. And so what's the voltage on capacitor 2 is Q naught over 3C. is equal to IR. So then I would be Q naught over 3RC. Did I do that correctly? I literally just walked around that pink loop right there, and I just came up with basically that equation. Does this affect anything? I think this is going to affect the amount of time it takes for the circuit to discharge, but we're not being asked about this. A long time later, all that stuff is discharged, and there is a path for these charges to also discharge. So I'm going to say we start with this current through resistor 2, but because this is here, it's going to take a little bit longer, and you know what? I'm not going to do that. Thanks for watching, and I hope I got the answers right, and if I didn't, you can put it in the comments, and you can flame me and whatever you want to say like that. But this has been a production of World's Finest Physics. Please consider if you'd like to come to my professional development or recommend my math development to the math teachers you know. All right, I'll see you over the weekend for P1 and P2.